Yeah, so I'm trying to figure out where some of the fundamental ideas in modern mathematics comes from. That's my dog in the background. He saw something, I don't know what, and now he is barking at stuff. And I don't like the way that that's set up. Cool. So the way I've been understanding this so far, for the most part, is that Modi, stop it. Come here, puppy. I know you see something. Do not worry. It is just another dog. It's quite interesting to go through and try and understand what's happening, because the narrative behind it's very much not linear. And you have to do a lot of reading of what people have tried to say about logic in order to get to where we are now. As far as I can tell, the way that logic starts out, or its original source comes from, is from Aristotle. And Aristotle came up with his version of logic, which is basically syllogistic inference, from what I can tell. And syllogistic inference is really useful for understanding certain things. There's a reason it lasted so long. But eventually, what ended up happening is that in the 19th century, people found out ways in order to generalize this to more abstract forms. And this happening eventually led to the development of set theory. And this is one of the things that I don't quite fully understand. So what I've read so far, what it indicates to me is one of the first things that we can see happening, and this is really important, is, and this is a fantastic book, for a reference book for understanding this stuff. It's basically this guy named, I don't know if they have him in here. Let's see, symbolical. Modi, stop it. Modi, come here. Modi! No! I should put the bark collar on him if he's like this, but it's not charged up. Modi! No! No! This guy named Peacock, Gregory Peacock, I think his name is, I want to say, Peacock, came up with this idea of symbolical algebra. And symbolical algebra was basically one of the first attempts to abstract mathematics into the realm of just symbols. And this was published in, let's see if it's in here. It was published in 1833, it looks like. Let me see if I can find it. Yeah. George Peacock was his name. Yeah, and he uses something called the principle of the permanence of forms. But like before this, if we look at the readings of people trying to understand mathematics, really the only person that did a detailed, like a really detailed understanding of what was going on, or a comprehensive version of what's going on, was Kant. Kant's, as far as I can tell, I think Kant is actually even right to the modern day, and I think you can justify him, but it's a little bit more complicated. You have to go beyond his initial thinking. But he basically analyzes mathematics, and he says that mathematics comes from what's called the intuitions of space and time. And intuitions, I don't like that word because you shouldn't use like a word that we have for something else to describe, a word that we commonly use for something completely separate to describe what Kant's talking about, because it's completely different. Intuition is kind of like the fire hose of experience. So it's kind of like, it's a very difficult concept to explain. I'm not sure the most straightforward way to do it, but it seems to me like the ground upon which we can use our it's basically the way our prefrontal cortex, or it's part of the method our prefrontal cortex is able to visualize three-dimensional shapes, and also how we're able to understand time as well. But as far as I can tell, it basically has to do with a lot with like mental visualization. And the way Kant thinks about mathematics is in terms of that. And I know that's not exactly precisely right, but that's kind of how he goes about it. And, you know, up until that point, you basically were dealing with Euclid. And Euclidean geometry was the ground upon, well, let's step back for a second. So we basically have Euclidean geometry, and Euclidean geometry starts with Euclid's Elements, and Euclid's Elements were published way back then. Elements. It was, I mean, published isn't even the right word. It was published 300 BC, so that's like ages ago. And basically, it's really the first axiomatic version of mathematics, as far as I'm aware of. I'm not sure if there's some other stuff that's happening in like India, for example. But you know, this is the gold standard for understanding geometry. And then on top of that, so this is the gold standard. We also have the development of arithmetic over time, and as far as I'm aware, we have, I guess that's a good question, actually. How did arithmetic develop? I'm aware that a lot of it has to do with geometry and the way of thinking about geometry. But I'm not sure where the ideas of using like symbols for arithmetic come from. So we have like these two branches of mathematics, I guess. And the question, to me at least, is, like from an abstract perspective, it seems like we have people really, really trusting in the Euclidean method, in Euclid's method in the Elements. And the question Kant tries to answer is, why is this method gives us certainty? And he gives a good answer as far as I'm concerned. He basically says and this is me oversimplifying, and I'm sure Kantian scholars would tell me that I need to get my get this completely rephrased, but as far as I can tell, he's basically talking about the universal ability for minds to visualize visualize what were encompassed in space and time. And he basically says that these are just intuitions, and whatever's out there, we can't necessarily identify with that's actually space and time. There's this whole entire debate about that. But the point is, right, he's trying to understand why Euclid was right, and he goes through and he understands, okay, here's like the fundamental ideas behind geometry relating to intuitions. And the other thing he's trying to do is he's trying to understand where logic comes from, because you basically combine logic and intuitions, and then you get Euclid's axioms, and it's all working out. Though I'm not sure, I'm pretty sure Euclid's axioms doesn't use Aristotelian logic. Euclid's Elements and Aristotle. Yeah. Yeah, so we didn't use it in there. So I guess I'm like where, so arithmetic, right? It originally deals with, from a historical perspective, it develops out of the need to do accounting, basically, like taxes and stuff like that, money. And which is interesting because that directly relates to some of the cognitive mathematics behind set theory, because it's kind of the cognitive mathematics behind set theory actually relates to how we perceive ownership in some sense. Um, that's a whole different ball of wax I don't want to get into. But what we more or less have is it develops out of that. But like, what's the foundational text behind arithmetic? Because there usually is one, and that's like the one that's studied. It's the standard thing that everybody uses until something new comes around and it changes what people think is the standard. So let me see. Emergence of arithmetic. Emergence of arith. Yeah. Plato Stanford. This is such a good source for understanding these things. Like, I want to read all of these, but I only have so much time. This is the one I'm basically trying to get through myself. Arithmetic. So I guess I shouldn't be using the term arithmetic. I should really be using the term algebra. Emergence of algebra. Yeah, not arithmetic. Okay, so there's a timeline here. Arithmetica. Like, what is the equivalent of Euclid's elements for algebra and arithmetic? Okay, so Arabic numerals come in at about 1202, which so in the 13th century we get Arabic numerals. So fucking like how many centuries is that? You could say that's like 13th century. That's like probably 8 centuries worth of time. They're just using the Latin method of calculation. Clearly much slower than anything else. Or Latin numerals, I guess you would call them. Interesting. Tools of algebraic symbolism. So 1202, we first get Arabic numerals. Like my guess is it takes another century for it to catch on. 1619, Descartes discovers analytic geometry, which that's interesting because analytic geometry is basically the application of like coordinate systems. Why did that take so long? Interesting. So analytic geometry is that with coordinates. So I'm going to try and understand this real quickly. So we have legiometry, or whatever you want to call it, legiometry. I bet you Stanford has a better version of this. Stanford. Here's what it is. Here's what it does. So Pappus's collection is related somehow. It has to deal with, like, I don't know who Pappus is, probably some like Latin 4th century Latin. It's just some Latin dude. So Descartes is kind of responding to this, I guess. Yeah, so like numbers, if we think from a cognitive perspective, the history of cognition, at first what they're used for is for, like I said, banking, ownership type purposes. And accounting is probably the better word for it. But then it's found that it can be applied to distances as well. So you basically abstract out from, I mean, like, yeah, accounting is the better way to think about it. You think about the utility of it. The utility was in regards to ancient finance. But it's discovered that it's extremely useful for geometry as well. But is it only for measuring distances in geometry? Then Descartes comes around, and what he does is he basically shows that it's not just distances that it's useful for, but it's also useful for labeling any position in space. I don't think he does time. That's probably where Newton comes in. I'll be right back. So if we're thinking about this from like the cognitive history of mathematics, um, the cognitive history of mathematics would be a good title. Maybe I should use it someday. Um, so for thinking from the cognitive history of mathematics, we don't have somebody who owns that first leap from numbers into geometry. It might be Euclid, but he's probably the popularizer. That's my guess. I mean, I'd have to know more about ancient Greek mathematics in order to understand where that came from. I mean, like maybe it came from like Persia or something like that. I don't want to give all the credit to the Greeks. That just seems a little bit wrong, considering that we had like a whole entire civilization in the Middle East before them. But for whatever reason, we have that. And then Descartes comes around and he realizes that not only can he use it for distances, and not only can you use it for distances, but you can also use it for describing any particular location, I think. This is where, if we go back for a second, right? Like this is kind of where I think it makes sense that people would be like flipped out about like irrational numbers if you were Greek at that point. Because there's this famous apocryphal story where it's claimed that the person who first showed that irrational numbers were a thing using basically the Pythagorean theorem got thrown overboard of a ship because of how shocking it was. Because he's essentially saying that there are distances that cannot be broken down into ratios, which basically means that distances in some sense can't be reduced to the integers that were used for more or less the accounting purposes that people cared about. Which basically means that geometry has its whole entire rule set different. And in regards to number than the standard application, which it's hard for me to understand the cognitive mechanisms that would shock people so much. I can understand the shock, weirdly enough, but I don't know if I can understand the cognitive mechanisms that would make it so shocking, because you're basically saying that you either accept that distances are described by numbers, and therefore there are numbers that are a completely different paradigm from what you thought before, or you're saying that distances are different in structure in some way from space, I guess, not necessarily distances, considerably from numbers themselves, if you just treat numbers in the accounting way. Either way, it's something that would be shocking. So going back to this, right, trying to understand Descartes. The ancients stated that there are three kinds of geometrical problems, and that some are called plane, others solid, and others line-like. And those that can be solved by straight lines and the circumference of a circle are rightly called plane. By straight lines and the circumference of a circle are rightly called plane because the lines by means of which these problems are solved have their origin in the plane. This is one thing where, like, I'm not sure quite whether to read it out loud because it makes it harder for me to process it at the same time. Maybe I read it and then I read it out loud afterwards. I guess he's saying there are different geometrical problems in regards to specific curves. You can use planes, solids, or line-like ways to construct curves. Yeah, I don't see this as being, I'm missing the context. I don't see this as being particularly important. He's making a classification schema, it seems like. Okay, what's the point? So we have Papas doing some stuff. So this is something that's probably going to be valuable to me at some point, but like, quite frankly, this is just like old geometry type stuff. Like, I don't really care about, oh no, we came up with some geometrical stuff. Like, how long even is the geometry? PD. 82 pages. I don't even know French. So whatever, he comes up with this, I'm trying to figure out something a little bit different. I'm trying to figure out where set theory comes from, like the modern development of mathematics, which, I mean, it appears to come from Russell and stuff, but like, there's something else that was going on there. I don't think that's a sufficient explanation for it. Just saying, oh, it was all Russell putting everything together. You did put a lot of stuff together, but there's something else going on. Okay, so anyways, we go to first order logic. Going back to logic, and this is where it all started, what we were talking about, trying to understand how logic and mathematics became so intertwined. Because you have this whole entire program. So Peacock comes up with symbolical algebra, the principle of the permanence of forms. So let's go back and let's read about this again. This is where it gets interesting, because like the foundations that we consider essential to mathematics, they weren't developed until like the very, very end of the 19th century. So we both have Argand and Gauss trying to justify complex numbers. And Argand, Sirwa, whatever this guy is. It's just about algebraic forms. At stake in these debates was not only the legitimacy of extending the number concept beyond the positive numbers, but also, as the quotation from Berkeley makes clear, the justification of the methodology of the differential calculus. So it's all about calculus again. Like, how do we put calculus on a firm footing that we actually think is legitimate? Because Newton has this whole entire geometrical method, and what's his face? I'm forgetting his name. Not Berkeley, it's... I should know this guy's name off the top of my head. Leibniz. Leibniz uses a much more algebraic approach. But there's no standard formulation for it. If I recall, Cauchy does the first, what we would recognize as an epsilon delta proof. There were versions of it like floating around beforehand but they weren't like unified in any way, shape, or form. But he writes it down in his book on calculus. but it's still not what we would consider standardized. Yeah. Yeah, so we have like continental versus non-continental. I guess this is why Maclaurin's definitions matter so much. Is it Maclaurin or Lambert? Yeah, so Maclaurin does response to the analyst to try and make it make sense using geometry. Disgusting.